Alright, so our next section is R6 exponents. And in truth, some of this review is a bit circular, right? We've already worked with exponents quite a bit, but in this section we'll do even more with them, and I'll remind you of all the rules of exponents and whatnot. And for starters, I'll remind you that exponents are to multiplication as multiplication is to addition, right? What do I mean by that? What is multiplication? When I say do 4 times 3, right, what does that mean? Well, 4 times 3 is really just shorthand for saying add 3 to itself 4 times, right? It's 3 plus 3 plus 3 plus 3, add 3 to itself 4 times, right? That's what multiplication means. It's shorthand for repeated addition. You could also flip the order here and think of this as add 4 to itself 3 times, right? So exponentiation has the same relationship as multiplication does with addition, but exponentiation has that relationship with multiplication. It means do repeated multiplication, right? So 4 to the power of 3, let's go the other way around. Let's do 3 to the 4, right? This means multiply 3 by itself 4 times. Right? So 3 times 3 times 3 times 3. Alright, so exponentiation is just the mathematical notation for repeated multiplication, just like multiplication is repeated addition. So, yeah, we'll go through the definition. What is a squared? Actually, let's do a to the 1. Alright, so a to the 1 means a multiplied by itself 1 time. Right, so it's just a. What's a squared? That means a multiplied by itself twice, so a times a. What about a cubed? That's a times a times a. Right, a multiplied by itself 3 times. And in general, a to the n would be a times dot 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 a n times. Right, a multiplied by itself n times, where n is 1, 2, 3, 4, whatever. A little bit more terminology. This guy here, the term a, this number a, this is usually called the base. And n is called the exponent. And you'll notice that I've only defined exponentiation for 1, 2, 3, 4, 5, 6, all of the natural numbers, right? So we define a to the 0. What does it mean to raise a number to the power 0, right? Multiply a by itself 0 times. What does that mean? Well, the way we agreed to define it is just anything to the power 0 is 1, with one exception. 0 to the 0 is not defined. Right? It's sort of like dividing things by 0, taking 0 to the 0, we just don't define it. It doesn't make sense. But anything else to the power 0 is always 1. And a to the minus n, so now I'm going to talk about negative exponents, something like a to the minus 3 or minus 5 or whatever. We define this to be 1 over a to the n. Alright, so negative exponents means 1 over a to the n. Alright, so just a handful of really quick examples here now that we've defined exponentiation. 18 to the power 0, what's that equal? Well, anything to the power 0 is 1, so it must be 1. 4 to the minus 3, what's that equal to? Well, 4 to the minus 3 by definition is 1 over 4 cubed. And 4 cubed is 4 times 4 times 4. So 4 times 4 times 4 is 64. So it's 1 over 64. And again, if you put that into a calculator, you'd get a decimal approximation. But quite often, something like my math lab will want the exact answer. So 1 over 64 would be the exact answer. And we'll just do one more. 2/3 to the minus 1. What's that? Well, that's 1 over 2/3. And how do you divide by a fraction? Well, you flip it and multiply, right? So this becomes 1 times, not 2/3, multiply by the reciprocal, 3/2. What's 1 times 3/2? Just 3/2. And in this case, you could enter 1.5 into MyMathLab because that's not a decimal approximation. 3/2 is exactly equal to 1.5. Alright, so the really important stuff. The really important stuff is that you know all the properties of exponents and that you can use them. So all of the properties of exponentiation, here's one we've been using already. If you've got two numbers with the same base but different exponents, a to the m times a to the n, how do you work with this? Well, you add the exponents together. So that's equal to a to the n plus n. Which shouldn't come as a surprise, right? This is just a times itself m times. This is a times itself n times. So how many times are you multiplying a by itself? M plus n times. Right? We've also used this one. A to the m over a to the n is a to the m minus n. Again, think about why this is true. Well, this is a times itself m times, and then I've got n of these products of a down here. I can cancel out n of them. How many am I left with? I'm left with m minus n. 3. A to the m to the n. And again, you could derive this formula on your own if you just thought about how many a's do I actually have in this giant product here. But the way you deal with repeated exponentiation is you multiply the exponents together. So that's a to the m times n. I don't really like the product sign there. We'll just write mn. It's understood they're multiplied. What about this? What if I have a product? So two numbers, a times b, right? My base can be thought of as a product, a times b to the m. Well, you can distribute this exponent to both bases. So this would be a to the m times b to the m. And similarly, if I write this as a quotient, a over b to the m, that's a to the m over b to the m. So there's all the important properties of exponentiation, and you should be able to use all of these properties. You should be comfortable with them and working with these properties when solving equations. Alright, so for example, here's just a simple one to start with. X to the power 3 over x to the 7. What does that equal? Well, using our rules of exponents, that's x to the 3 minus 7, right? And 3 minus 7 is minus 4, x to the minus 4. And I guess you could leave it like that, but a slightly nicer form than having a negative exponent would be 1 over x to the 4th, right? Because negative exponents means 1 over. By the way, not the only way you have to think about solving this. Here's another way you could have solved this. You could have said this is x cubed over x to the 7, well 7 is 3 plus 4, right? So I could write this as x to the 3 times x to the 4, because multiplying them gives me x to the 3 plus 4, which is 7 again. And then I could cancel those guys out, and I'd be left with 1 over x to the 4th. So there's many ways to proceed when you're doing algebra, quite often. How about this one? We'll just simplify a to the minus 3 times b to the 5th over a to the 4th times b to the minus 7. Alright, so I want to simplify this. And what I'm going to do is I'm just going to work with the a's and the b's separately. So let's just completely separate these two expressions. So I've got a to the minus 3 over a to the 4th. And what I could do is I could write this as a product, so times b to the 5 over b to the minus 7. Right, I'm certainly allowed to do the separation because multiplying products or multiplying fractions just means multiply the tops together and the bottoms together to end up right back here. Why did I do that? Because I want to work with these separately. I want to think about the a's and the b's separately. So a to the minus 3 over a to the 4, that's a to the minus 3 minus 4. Right, you subtract the bottom exponent from the top. And times, we've got b to the 5 minus 7. So what do we actually have here? We've got a to the minus 7 times b to the 5 minus 7 is 5 plus 7 is 12. So that certainly looks a whole lot more simplified than what I started with, right? And one more thing I could do, again, negative exponents are a little bit ugly, so we'll write this as b to the 12 over a to the minus 7, puts the a to the 7 on the bottom there. Alright, so all I did was simplify. I just, I took this expression we started with and I simplified by canceling out some of the redundant powers. We'll just do one more. Let's say I've got r to the minus 1 plus s to the minus 1. And someone might look at this and they might honestly say this is simplified, right? And the truth is, simplification is in the eye of the beholder. This is a pretty simple expression, but I'm going to manipulate this, right? The goal is to just work with exponentiation and manipulate it. So r to the minus 1 means 1 over r. S to the minus 1 means plus 1 over s. And what I usually do with fractions is I write them as a single fraction, right? So I combine them into a single fraction. So I want to put these over a common denominator. Least common multiple of r and s would be r times s. So we'll multiply top and bottom of this one by s, top and bottom of this one by r, and now they're both over r times s, right? So this is s over rs. S times r, you can write that as r times s, the order doesn't matter, plus r over r times s. Or s plus r over rs, right? Once they're over a common denominator, you can now combine them into a single fraction. Cool. So that's the easy part of exponents. Well, let me not say the easy part, but it's the whole number version. What we haven't talked about, right, we've talked about powers of 1, 2, 3, 4, 5, we talked about powers of 0, powers of minus 1, 2, 3, 4, 5. What if you have fractional exponents? Right, so this is where we're going. How do you work with fractions? And we'll make our definition now. So, what does this mean? A to the 1 over n equals b. Well, we define a to the 1 over n to equal b if and only if b to the n is equal to a. Alright, so if and only if, when you raise b to the power n, multiply b by itself n times, you get a as your output. Alright, so in other words, this is sort of a backwards definition, not necessarily backwards, but a very introductory definition, because we haven't really worked with radicals and square roots yet or anything. But in other words, I'll just jump right into it. A to the 1 over n is the positive nth root of a. Right? Why? Because it's equal to some number that when you multiply by itself, or multiply it by itself n times, you get a back. So a to the 1 over n is the positive nth root of a. That's what an nth root is. It's the number that when you multiply it by itself n times, you actually get a as your output. And so, for example, 27 to the 1/3, this represents the cube root of 27, right? What number do you multiply by itself 3 times to get 27? Well, 3 times 3 times 3 is 27, so the 27 to the 1/3 is 3. Let's see. 100 to the 1/2, what is the square root of 100, right? What number do you multiply by itself to get 100? 10. Now we'll just do one more. 64 to the 1/6. The 6th root of 64. What do you multiply by itself 6 times to get 64? Turns out it's 2. Right? So multiply 2 by itself 6 times, you will get 64. So we still need to ratchet this up one more notch. We've only dealt with 1 over n. What if I have something else in the numerator, right? What if I've got m over n? Alright, so we'll define that. Define a to the m over n. How do we define this? What does this mean to raise something to something like 5 over 4 or 10 over 12 or this would be, we define this as a to the 1 over n, which we've already talked about, right? It's the nth root of a to the power of m. Or, right, turns out you don't have to go that route. It's the same as defining this to be a to the m, right? So raise it to the m first, to the 1 over n. Right? Because what does repeated exponentiation mean? The way you do repeated exponentiation is you multiply these two together. And m times 1 over n is m over n. And 1 over n times m is m over n. So this is our definition for complete fractional exponentiation. And so, for example, what if I wanted 27 to the 2/3? And most of you would probably be completely content just plugging this straight into your calculator, right? And there's really nothing exactly wrong with that because you're allowed to use calculators, but you should be able to handle expressions like this in your head or just very quickly doing some quick scratch work, right? Because it is a nice number and you don't need a calculator to do it. Alright, so by definition, this would equal 27 to the 1/3 squared, right? Write the 2 on the outside. So 2 times 1/3 is 2/3. And now if I just go step by step, right, instead of trying to do this 2/3 power all at once, I break it into 2 pieces. We already saw a cube root of 27 is 3. So this is 3 squared. And 3 squared is 9. So 27 to the 2/3 is exactly equal to 9. And I didn't need a calculator to do it. By the way, if you went the other route, or I could have said, this is 27 squared to the 1/3, but that doesn't really help me if I'm trying to avoid calculators, right? Squaring 27 in my head, or even just writing it down, this product takes a while to do, right? I don't know what 27 squared equals. And once I have it, it's a huge number. I don't know what the cube root of that huge number is. So you have freedom in the order that you choose to do this, right? Do you bring out the numerator or do you bring out the denominator? But using that freedom, try to choose the better way. So really quickly, 32 to the 2/5. Again, pause the video if you want, right? Try and work this out on your own without using a calculator. I'm going to choose, again, not to square 32. All right, this is 32 to the 1/5 squared. So we'll write it this way. And that's because the fifth root of 32 is pretty easy to compute. Fifth root of 32 is just 2. So that's 2 squared, which is 4. Alright, so there's 2 more types of problems you need to be able to work with. So we'll simplify something involving fractional exponents now. Let's say simplify x to the 1/2 times x to the 4th over x to the 3/2 times 1/3. And before I get going, again, I don't claim this is the only way to proceed, the way I'm going to go, but I do think it's the easiest. But there's lots of other things you could do. You could, for example, multiply all these powers by 1/3 if you wanted to. Right? That's the first step you could do. But that's actually the last step I'm going to do. For now, I'm just going to combine all this stuff. Right? So this is x to the 1/2, multiplying these together, I add the exponents, right? So x to the 1/2 plus 4 over x to the 3/2 to the 1/3. And now, I guess I could add these together. That would be 9/2, right? 4 plus 1/2 is 9/2, but let's do this all in one go. This is x to the 1/2 plus 4, and then I'm dividing by 3/2, so that's minus 3/2, right? Minus 3/2 to the 1/3. So what is this? 1/2 plus 4 minus 3/2 is x cubed, I believe. Right? 1/2, 4 minus 1 is, yeah. This is just x cubed to the 1/3. And last but not least, 3 to the 1/3, you multiply them together, 3 times 1/3 is 1. So it's just x. So this entire complicated looking expression is actually much simpler. There's no reason to write like this. It's actually equal to just x itself. Now we'll do one more example. Factor 5x to the 1/3 plus 10x to the minus 2/3. So I want to factor this. And what you'll notice is, okay, I've got 5 common to both of them, so I can pull out a 5, that's fine. But I also have powers of x common to both of them, right? So I want to pull out some power of x. And the question is, what power of x do I extract, right? And there's actually no sort of necessary way to do this, right? But there is an agreed upon way that tends to work the best, which is when you've got a whole bunch of powers of x, including negative powers, you pull out the smallest power that you see, right? So the most negative power that you see. And in this case, I've got x to the minus 2/3 is my smallest power. So that's what I'm going to factor out. We agreed we'd pull out a 5 too, right? So we'll pull out a 5, and we'll pull out x to the minus 2/3. Okay? So if I pull out x to the minus 2/3 in this one, right, if I factor it out, that means I'm just dividing by it. Right, that's one way you could think about this. I won't ever write this step again in the future, but when I say factor out an x to the minus 2/3 from this, I mean I'm really dividing it out. Right? I'm just dividing through, because when you multiply these together, you'll end up right back at x to the 1/3. Here I pulled out a 5 from the 10, so I'm left with 2. And I've already pulled out the x to the minus 2/3. Right? If I want to be very formal, I could write this as x to the minus 2/3 over x to the minus 2/3, but I think it's pretty clear that I don't need to. Alright, so the last step is just simplifying the inside here. 1/3 minus minus 2/3 is 1. So x to the 1/3 over x to the minus 2/3 is just x to the power 1 plus 2. So like I said, I will skip this middle step in the future, right? I won't write this. When I pull out x to the minus 2/3, how am I figuring out what power for x I should have here? Well, I'm just thinking, what number, when I subtract 2/3 from it, will give me 1/3, right? And in that case, it's 1. Right? Because when I subtract 2/3 from 1, I get 1/3 as my output. So that's how I find this power. Now, I think there's lots of questions like this in the homework, and just in the future in this course is you'll have to deal with factoring out expressions like this. So if you see a negative power, always go to the smallest negative number you see, the most negative number, and choose that as your factor. Okay.